In the previous topic, we have learned various characteristics of a chemical equilibrium. For the following reversible reaction, 2 moles of NO2 gas gives 1 mole of N2O4 gas. We learned that at equilibrium, the concentration of reactants and products remain constant over time. 2. The rate of forward reaction is exactly equal to the rate of reverse reaction. The rate of forward reaction can be written as K forward times the concentration of NO2 to the power 2, where K forward is the rate constant for the forward reaction. In the same way, the rate of reverse reaction can be written as K reverse times concentration of N2O4 to the power 1. If we simplify this, we get K forward over K reverse is equal to the concentration of N2O4 divided by the concentration of NO2 to the power 2. The ratio of two rate constants can be written as a new constant, capital K, which is called as equilibrium constant. Capital K is equal to the concentration of N2O4 at equilibrium divided by the concentration of NO2 at equilibrium raised to the power 2. This is called as equilibrium constant expression or law of mass action. Let us now properly define law of mass action or equilibrium constant expression. For a hypothetical reaction, A moles of A reacts with B moles of B to form C moles of C plus D moles of D. The equilibrium constant K can be written as AC to the power C times AD to the power D divided by AA to the power A times AB to the power B, where small a is called as activity or active mass and A sub C means activity of C and A sub D means activity of D, and so on. For a particular reaction at a particular temperature, the equilibrium constant K is a constant. So, what is activity or active mass? For an aqueous solution of reactants and products, the activity A is equal to the molarity of the species, that is reactant or product, divided by molarity of a reference solution. The molarity of a reference solution is taken as 1 molar. So, if the hypothetical chemical reaction we discussed earlier occurs in an aqueous solution, the equilibrium constant K can be written as molarity of C times 1 molar raised to the power C, molarity of D divided by 1 molar raised to the power D, and so on. However, when we are writing the equilibrium constant expression, we don't always represent the molarity of reference solution in the denominator. Since we are dividing each concentration term with the concentration of a reference solution, the equilibrium constant K is a dimensionless quantity. That is, it does not have any units. Let us do a quick example. Calculate the equilibrium constant for the following reaction at 27 degrees Celsius. 1 mole of nitrogen gas reacts with 3 moles of hydrogen to form 2 moles of ammonia gas. The equilibrium concentrations of reactants and products at 27 degrees Celsius are given below. Concentration of nitrogen at equilibrium is 0.3 molar. Equilibrium concentration for hydrogen is 0.35 molar and equilibrium concentration of ammonia is 0.18 molar. First, let us write down the equilibrium constant expression or law of mass action from the balanced chemical equation. Equilibrium constant for a chemical reaction is equal to the equilibrium concentration of products raised to the power of its stoichiometric coefficients divided by the equilibrium concentration of reactants raised to the power of its stoichiometric coefficients. So, equilibrium constant K is equal to the concentration of ammonia at equilibrium, and its stoichiometric coefficient is 2, divided by concentration of reactants, that is nitrogen at equilibrium, and its coefficient is 1, and concentration of hydrogen at equilibrium, and its coefficient is 3. The equilibrium concentration of all the reactants and products are given. Let us now plug in the equilibrium concentrations into the equilibrium constant expression. If we do the math, we get equilibrium constant K is equal to 2.58. As we mentioned earlier, it is a dimensionless quantity. Let us now discuss some important points about equilibrium constant and equilibrium concentrations. For example, we have a hypothetical reaction A gives B, and we have performed several experiments and measured initial and equilibrium concentrations of A and B. From the equilibrium concentrations of A and B, we calculated the equilibrium constant K. For example, in experiment 1, we started with 0.1 molar A and 0 molar B, and the equilibrium concentrations are 0.5 molar A and 0.5 molar B. If we calculate the equilibrium constant, which is equal to equilibrium concentration of B over equilibrium concentration of A, we will get 1. In experiment 2, we started with 0.1 molar B and 0 molar A. The amount of B that I am using in experiment 2 is same as when all A in experiment 1 is converted to B. And the equilibrium concentrations are 0.5 molar A and 0.5 molar B. The equilibrium concentrations for experiment 2 are same as experiment 1. Since we are starting experiment 2 with stoichiometrically equivalent concentration of B, and the equilibrium constant for experiment 2 can be calculated as 1. In experiment 3, we start with 0.5 molar A and 0 molar B, and the equilibrium concentrations are 0.25 molar each. Equilibrium constant is 1. In experiment 4, we have both the reactants at the beginning, that is 0.5 molar A and 0.7 molar B, and the equilibrium concentrations are 0.6 molar A and 0.6 molar B. Equilibrium constant is 1. There are a couple of important points that we can make here. 1. The equilibrium constant for a particular reaction is always the same as long as the temperature of the reaction is kept constant. Point number 2. As you can see, the equilibrium concentrations are not always the same. The equilibrium concentrations of reactants and products depend on the initial concentration of reactants and products that we are starting with. Therefore, we can say that for a particular reaction at a particular temperature, there is only one value for equilibrium constant. That is, K is unique. However, there are infinite number of equilibrium concentrations depending on the initial concentration of reactants and products. Let us now discuss what happens to the equilibrium constant when we manipulate the chemical equations. The value of the equilibrium constant for a particular reaction depends on the direction in which the given reaction is written. The following is the chemical equation for the production of ammonia using Haber's process. Nitrogen gas reacts with 3 moles of hydrogen gas to form 2 moles of ammonia gas. Earlier, we have written the equilibrium constant expression for this reaction. K is equal to the concentration of products over reactants, that is, the concentration of ammonia at equilibrium raised to the power 2 divided by concentration of nitrogen power 1 and concentration of hydrogen at equilibrium power 3. Let us now reverse this reaction and write the equilibrium constant expression. So the products of the above reaction becomes the reactants, and the reactants of above reaction becomes the products. 2 moles of ammonia gives 1 mole of nitrogen and 3 moles of hydrogen. Let us now write the equilibrium constant expression for this reaction. The equilibrium constant, let us call as K prime, is equal to the concentration of products over reactants, that is, concentration of N2 at equilibrium power 1 times concentration of H2 at equilibrium power 3 divided by the concentration of NH3 at equilibrium power 2. Let us now express the new equilibrium constant K prime in terms of the old equilibrium constant K. As you can see, this value can be written as 1 over K. In other words, we can say that if we flip a reaction, the equilibrium constant of the new reaction is reciprocal to that of the original reaction. Next, let us multiply the equation for Haber's process by a number 2 and then write its equilibrium constant expression. 2 moles of nitrogen reacts with 6 moles of hydrogen to form 4 moles of ammonia. Next, let us write its equilibrium constant expression. Equilibrium constant K double prime is equal to the concentration of products divided by concentration of reactants, that is, concentration of ammonia at equilibrium raised to the power 4 divided by concentration of nitrogen raised to the power 2 times concentration of hydrogen raised to the power 6. Let us now express our new equilibrium constant in terms of old equilibrium constant, which comes out to be K power 2. That is, if a reaction is multiplied by a number, the equilibrium constant of the new reaction is equal to the original equilibrium constant raised to the power of the number multiplied. Next, let us learn what happens to the equilibrium constant when we add two different reactions. For example, we have the following reactions. 1 mole of hydrogen reacts with iodine to form 2 moles of HI. The equilibrium constant for this reaction, K1, is equal to the concentration of HI to the power 2 divided by concentration of H2 and I2 at equilibrium. The second reaction is I2CO gas dissociates to produce 1 mole of iodine gas and 1 mole of carbon monoxide gas. The equilibrium constant for this reaction, K2 is equal to concentration of I2 times concentration of CO divided by concentration of I2CO. Let us add these reactions together. I2 on the reactant side and I2 on the product side gets cancelled. The overall reaction is I2CO gas reacts with hydrogen gas to form 2 moles of HI and 1 mole of carbon monoxide gas. Let us now write the equilibrium constant expression for this overall reaction. K nu is equal to the concentration of HI squared times concentration of CO divided by concentration of I2CO times concentration of H2 at equilibrium. Let us now try to express the new equilibrium constant K nu in terms of K1 and K2. If we do the math, we get K nu is equal to K1 times K2. So we can say that if we add multiple reactions, the equilibrium constant of overall reaction is equal to the product of all the reactions that are added.